Welcome to the second live session of Nuclear and Particle Physics course. So we will be solving assignment 2. Okay, so let's get started. The first question asked what is the expected spin value of the ground state of this nucleus within the nuclear shell model. I'm audible, right? Hello, can someone respond? Yeah, okay. So in order to understand this nuclear shell model, let us first this nuclear shell model is basically motivated by the atomic shell model. So we know that when we consider a particular atom, the electrons of that atom move due to the potential generated by the nucleus, and the electrons of a particular atom can be accommodated in what we call atomic shells. So these electrons are accommodated in the atomic shells. Right? So for example, the simplest example, the neon, that was also considered in the lecture. So it has 10 electrons, and these atomic shells are labeled by what we call principal quantum numbers, small n. So small n can be 1, it can be 2, 3, etc. So small n equal to 1 can contain at most 2 electrons. This n equal to 2, 8 electrons, and so on. So if we are considering neon, for example, then it has so this is consider this to be nucleus, and then n equal to 1 shell contains 2 electrons in it, n equal to 2 shell contains 8 electrons in it, right? So that's why it is completely filled, and this entire thing is what we will call inert core. Whereas if we consider sodium, then this same configuration is there, apart from one more electron. So sodium has z equal to 11. So there will be one more atomic shell, n equal to 3, and that contains 1 electron, right? So this n equal to 3 for sodium is the valence shell, and almost all the properties of this particular atom, sodium, will be dictated by this valence electron. This one electron is called valence electron. Okay. Now this same kind of thing will also happen for the case of nucleus. So so far we are talking about atom, and these are electrons moving around that nucleus. So if we consider nucleus, this same picture should also hold. That's what the claim is. So, and that is what will be called nuclear nuclear shell model. So and the particular nuclear shell model that has been considered here is the extreme independent particle model. So what it states that for any odd A nuclei, the property of the nucleus will be dictated by the unpaired nucleon. Okay, so yeah, so it is just like this atomic shell model in the sense that here the valence electron dictates the property of that atom. So valence electron is the electron in the incompletely filled shell of that atom. In the same way, this nuclear shell model, under which we are considering this extreme independent particle model, here it states that for any odd A nuclei, the property of that nucleus will be dictated by the unpaired nucleon. Okay, so this particular concept will be used for the first three problems. So here we are asked to find out the spin value of the ground state of this nucleus. Okay, so in this nuclear shell, this independent extreme independent particle model, the neutron and proton will be considered separately, in the sense that suppose, okay, so since we are talking about odd A nuclei, so that means if Z is odd, then N has to be even, and if N is odd, then Z has to be even. So that's why these two, Z and N has to be considered separately. So for the case at consideration, this particular nucleus, so which particular nucleon are we supposed to consider? Since we will be dealing with unpaired nucleon, so for this particular nucleus, what do we supposed to consider? Neutron or proton? So what is the neutron number? 5 minus 7, that is 8, and proton is 7. So are we supposed to consider neutron or proton in order to answer this question? Okay, so the thing is, we have to consider proton, because proton will have one unpaired shell, one unpaired proton will be there in the atomic shell. So okay, let me draw the diagram. So the atomic shells this is 1 is half, this is 1p half, 1p 3 half, then 1p half, 1d 5 half, 2s half, etc. Okay, so before I answer this question, so S means L equal to 0. These things you know, but let me just say this. P means L equal to 1. So L is the angular momentum quantum number. D means L equal to 2. F means L equal to 3. Okay. Now one more thing, for a particular level, so of angular quantum number L, a particular level of angular quantum number L can accommodate 2 times 12 plus 1 number of nucleons in it. Okay, so for example, let us consider D level. So it means L is equal to 2, which implies D can contain within it 2 times, which is equal to 2 times 5, that is 10 nucleons in it. Moreover, the J value for D level can be L plus or minus half. So this half comes because of the spin of the nucleon. So nucleons are of spin half. So for D level, the J value can be either two plus half or 2 minus half. So 2 plus half is 5 by 2 and 2 minus half is 3 by 2. Okay, that's why for D we have 1D 5 by 2 and 1D 3 by 2. Okay, and any particular level like 1D 5 by 2 can contain two times 5 by 2 plus 1, or 2J plus 1. So these are the J values that D can take. J is either 5 by 2 or and J can be 3 by 2. J plus 1 nucleons. So for 1D 5 by 2, there can be at most that is 6 nucleons. Okay. Likewise for 1D 3 by 2, there can be 4 nucleons. The same thing happens for all these levels. So for 1 is half, how many nucleons can we put here for 1 is half? Can someone answer? Yeah, okay. That's right. So for 1 is half, we can accommodate 2 electrons. Likewise for 1p, 3 half, 2 times 3 half plus 1, that is 4 electrons can be accommodated in this level. Likewise for 1p half, we can accommodate 2 electrons. Here we can accommodate 6 electrons, and so on. Okay, this is in general, I am drawing it in general, not for this particular nucleus. So when we are considering this nucleus, the diagram will be we are having z equal to 7, so we are now considering for this nucleus we need to consider protons, since proton number is odd here, and one p half level there will be one unpaired electron, proton I mean, yeah. So that's why, and what nuclear shell model dictates, it says that for any odd A nuclei, the property of the nucleus will be dictated by the unpaired nucleon. So here the unpaired proton is in 1p half level, which means the spin of the, so this is the ground state configuration. Okay, we are not yet talking about excited states. We will come to the excited states in the third problem. So someone has asked already to explain excited states in shell model. I will do so, just wait for a few minutes. So this is the ground state configuration of nuclear shell model. Okay, so since the unpaired proton is in this particular level, the spin of the ground state is half. So this notation you understand right now, I hope. So let me say that again. So 1p half, it means this half denotes the spin, or which we denote by J, and this p means angular momentum quantum number L is equal to 1. Okay, fine. So the answer is B. We were asked what is the expected spin value of the ground state of this nucleus within the nuclear shell model. So since we see that the unpaired proton is lying in the state 1p half, that means the spin of the ground state will be half. So that's why answer B is the correct option. Do you have any doubt so far whatever I have said? Is this clear? Or should I explain again? Okay. Okay. Let us move on to the next question then. What is the expected parity of the ground state of this nucleus? Now you should be telling me here. Okay, so for silicon, Z is 14 and neutron number is 15. So in order to answer this question within this nuclear shell model, which particular nucleon are we supposed to consider? Proton or neutron? Neutron, because neutron is odd here. So, and we also need one more property, the relation that the parity of any state is related, how the parity of any state is related to angular momentum. Minus 1 to the power L. So if that is even, if that comes out to be plus 1, then we say that the parity is even. If that comes out to be minus 1, then parity is odd. So let us look at how the nuclear shell model looks like for silicon. Okay. Let me draw it. So, okay, first is one is half. It contains again two neutrons. Then 1p half. 1p 3 half. So there will be 4 neutrons. 1p half contains 2. Right. Then there is 1d 5 half. So it contains 6 neutrons, and then the 2s half. So there will be 1 neutron here, right? So the unpaired neutron is in 2s half level. So what does it mean? So looking at this expression, what can you say about the angular momentum quantum number? What is L? So you need L, right, in order to answer the parity of the ground state. So this is again the ground state configuration. Silicon 29, 14. Okay, and the unpaired neutron is in this level. So what is L for the unpaired neutron? L is 0 because it is S state. So that means the expected parity expected parity of the ground state will be minus 1 to the power L. L is 0, so that is plus 1. So the answer is A, even. Okay. Okay. If no doubts, I will move on to the third question. Okay. So within the nuclear shell model, the spin and parity of the first two excited states of magnesium are which one? Okay. So for magnesium, Z is 12, N is 13. So that means we have to consider neutron, because neutron number is odd, and we have to ultimately look at the unpaired nucleon. So for proton there cannot be any unpaired nucleon, because N is odd. We have to consider N because there can be one unpaired neutron, okay, which we can take to the higher levels in order to get the excited states from the ground state configuration. So in order to draw the excited states, let us first draw the ground state configuration. And okay, so again, so we need to accommodate 13 neutrons within this nuclear shells. One is half, there will be two, sorry, not, did I say electron? Okay, 13 neutrons, 3 half, so 4, and then it will contain 2, then 1 D 5 half, okay, yeah, so 5 neutrons will be in this state. So one particular neutron will be unpaired, and all others will be paired. Okay, so this is the ground state configuration. Magnesium. In order to get the first two excited states, okay, so the next level is 2s half, and then we have, I think, 2f, okay, 2s half, then 2d 3 half. Okay, so the first excited, to get the first excited level, first excited state, we will take one particular nucleon from 1d 5 half to 2s half. So this will give us the first excited state, and we are supposed to answer the spin and parity of the first two excited states. So what is the spin? The unpaired neutron is in 2s half level, so that means the spin is this half, right? And we also need to answer what is the parity. So again, S means L equal to 0, which means parity will be minus 1 to the power 0, that is plus 1, or even parity. Okay, and likewise for the second excited state, instead of taking the unpaired nucleon from 1d 5/2 to 2s half, now we need to take this unpaired nucleon neutron to 2d 3 half to get the second excited state. So okay, we now take the unpaired neutron to 2d 3 half, so that will give us the second excited state of magnesium. So right now the unpaired neutron is in 2d 3 half, so that means the spin of second excited state is 3 half, and d means L equal to 2, so which implies parity will be plus 1, that is even. Fine. So the person who was asking to explain the excited states of nuclear shell model, is this clear? Who was asking? Okay, so the correct answer would be this B option. Any doubts on this problem? Okay. Consider the classical case of a particle of mass 10 to the minus 30 kg and charge 1.6 into 10 to the minus 19 coulomb, moving in a circle with angular momentum 10 to the power minus 34 joule second. The magnetic dipole moment associated with this is question mark. So we know how magnetic dipole moment is related to the angular momentum, right? So that expression has to be used. So basically, if we have a charged particle, let me say this quickly, if we have a charged particle of charge q which is moving with a velocity v in a circle of radius r, then the time period, which is the time taken by the charge q to traverse a distance 2 pi r with velocity v, is the time period t equal to 2 pi r over v. Now the current within that circular loop will be dq over dt. So q over the time period, so 2 qv over 2 pi r, that is the current due to that moving charge. Now, how magnetic dipole is related? So the angular momentum, in order to find out that, we know that the magnetic dipole moment current times area. Area of that loop, so QV divided by 2 pi r times pi r square if we consider a loop of radius r. So mu is equal to QV divided by 2 r. Now we want to write it down in terms of angular momentum, because angular momentum is what is given to us in the question. So, and we know angular momentum is mvr, so we multiply numerator and denominator by m to write it in this form, q over 2m times L, angular momentum. So then q is known, given 1.6 into 10 to the minus 19 coulomb. 2 m is also given, the mass of the particle, 10 to the power minus 30 kg, and L is 2 into 10 to the minus 34 joule second. So mu will be come out to be, if you calculate this, you will get 1.6 into 10 to the minus 23 ampere meter square. Okay, so the correct answer is A. Okay. So basically you just need to remember this formula to answer this question. Okay. Let us move on to the fifth one. In a scattering of electron of a nucleus, electrons of energy 10 MeV are used if these electrons are represented by the wave function where the position coordinate is along z direction. What is the value of k? Okay. So we need to use, so for a plane wave, the energy momentum the relation between energy and momentum is h cross square k square over twice m. Okay, so basically from there we need to find out k. The value of k will be square root twice me divided by h cross square. E is 10 MeV, so square root of consider mass to be MeV per c square. Since h cross and 10 to the power 6 electron volt, so basically into E is 10, but then h cross is given in electron volt, so better to convert numerator in electron volt. So 10 to the power 12, 10 to the power 6 comes from m, and 10 to the power 6 comes from E, divided by h cross 6 point square. So it will be in the unit of meter inverse. Okay, if you calculate this, you will get 1.61 into 10 to the power 13 meter inverse. Is this fine? Are you not able to unmute yourselves? Like, is there any restriction or? Okay, you can unmute yourself, right? Fine. How we consider the mass value? So, okay, so here electron is given, right? So, we have just considered the mass of electron in MeV units. So, mass of electron is 9.31 into 10 to the minus 30. Okay. Okay. Mass of the electron. Fine. Since we are considering scattering of the electron of the nucleus. Okay. Sixth question. In an experimental measurement of the orbital angular momentum of deuteron, 10,000 samples were selected. Approximately how many of them would have measured L equal to 2H cross? Okay, so from the last live session, like we have told that deuteron can take the angular momentum value L equal to 0, 96% with probability 96%. And L equal to 1 it can take with probability 4%. Sorry, L equal to 2 in the unit of H cross. So in this problem we are asked how many of them would have measured L equal to 2H cross. So we need to use this 4% probability on this sample. So 10,000 samples were selected. So out of those, 4% of those will give the angular momentum 2H cross. So that means 400. Would have measured L equal to 2H bar, and the remaining, that is 10,000 minus 400, which is equal to 9,600, would have measured L equal to 0. But we are asked L equal to 2H cross, so D is the correct option. Right? Okay. Okay. So, okay. I want you to answer this question to me. Which of the following statements are correct? Wood's action potential adequately represents the nuclear potential in shell model and reproduce all the magnetic numbers observed up to Z equal to 100. If you have gone over the lecture, you must know this. Is this correct? Is this A option correct? Can this Wood's action potential adequately represent nuclear potential in the shell model and reproduce all the magnetic numbers observed up to Z equal to 100, or is it false? Okay, one person has answered. Someone else? Is it true or false? Okay. 2% are saying true. Well, but it is not true, it is false, because we know that Woods action potential cannot adequately represent all the magic numbers observed up to z equal to 100. In order to do so, we have to include the spin orbit coupling with the Woods action potential. So that is if the potential is Woods action potential plus the spin orbit coupling, then only the nuclear shell model, this potential can reproduce all the magic numbers observed up to z equal to 100 within this nuclear shell model. Okay, so A is incorrect. What about B? Extreme independent single particle shell model explains the observed spin and parity sites of the ground state of almost all odd A nuclei. So this is what we were using, right, in our problems. Extreme independent single particle shell model for the first 3 problems. So these are the 3 nuclei that we have considered in this assignment itself. So is it true? Okay, someone has said yes. Yeah, so this is true, that this particular model, so we have considered always odd A nuclei, right, and this extreme independent shell model helped us to explain this the spin as well as parity of the ground state. Okay, so B is correct. C says the collective properties of all the nucleons in the nucleus is more important in the case of even Z even N nuclei compared to the odd A nuclei. Well, so far we have only considered odd A nuclei, and for odd A nuclei we have only considered the unpaired nucleon, the unpaired nucleon at the topmost shell, nuclear shell, outermost nuclear shell. So, but if we want to consider this collective property of all the nucleons, if we consider even Z even N nuclei, that means this A will no longer be odd but it will be even, then this collective property of all the nucleons becomes more important. So this is actually true. Okay, for even Z even N nuclei that we have not dealt with in our problems, but if it is even Z even N, then collective property of the nucleus becomes more important. Okay, and D option is saying collective properties of all nuclei in the nucleus is more important in the case of odd A nuclei. Of course, that is not true, because we have considered odd A nuclei and have seen that we can say about the spin and parity of the ground state as well as for the excited state in terms of just the unpaired nucleon, and so collective property of all nucleon is not required for odd A nuclei, so this is incorrect. Okay, this 8th question is actually, answer to this question is given in lecture 7, so which is the week 3 lectures, but this question is given in this second assignment itself. So let me say this briefly. So the question is, which of the following statements is correct? Okay, both calcium 41, calcium 43 have a few low-lying excited states with excitation energy less than 2 MeV. The first excitation energy of calcium 41 is close to 2 MeV, while for calcium 43 has a few excited states with energy smaller than 1 MeV. The first excitation energy of both are around 2 MeV, and calcium 43 has many low-lying excited states below 2 MeV, indicating that the extreme independent single particle shell model need correction. Okay, so let us look at the nuclear shell model of these two nuclei, calcium 41 and calcium 43. So okay, so proton number is 20 for both. So basically for both these isotopes we have to consider neutron number, which is 21 for this case and 23 for this case. So the diagram, if I draw, let me draw here. So we need to draw 21 neutrons within this shell model. So 2 will be in the first level, then 1p 3/2 will contain 4, 1p half contains 2, okay, then 1d 5/2 contains 6, 2s half, there will be 2, then again 4, 1f 7/2, okay. So for calcium 41 the neutron number is 21, so the last level, that is 1f 7/2, will contain 1 neutron, and for calcium 43 this configuration will be the same, apart from the fact that now 1f 7/2 will contain 3 neutrons. Okay, so these are the ground state configuration for calcium 41 and calcium 43. Now so basically the ground state will have spin for both these nuclei. Ground state will have spin 7/2 and parity will be, so if means L is equal to 3, so that means -1 to the power 3, that is -1, odd parity, and spin of these is again 7/2 because unpaired nucleons, unpaired neutrons are in this 1f 7/2 level for calcium 43 as well, so that is again 7/2 minus, so these two are the ground states. Now all these options are talking about excitation energies. So okay, so for in order to get the excited states, as we saw that this particular nucleon has to be taken to some excited level, I mean some upper level. So for calcium 41 this neutron will be taken to 1p 3/2 in order to get the first excited state. Likewise for this 43 calcium, this unpaired neutron has to be taken to 1p 3/2. So we can guess that the unpaired we can guess that the excited state, okay, so let me draw the excited states as well. this is the ground state for both, that is 7/2 minus, and this is also 7/2 minus. This is calcium 41, this is calcium 43. Okay, around 2 MeV for calcium 41, there is first excited state, which is 3/2 minus. How you will get that? If we take this over here, then the unpaired neutron will be at 1p 3/2. That's why its spin will be 3/2 and parity will be minus, because p has L equal to 1, that is minus 1 to the power 1, which is minus 1, that is even parity. So the first excited state then should be 3/2 minus for calcium 41 20, and we would expect the same thing to happen for calcium 43 as well. Like if we take unpaired neutron from 1f 7/2 to 1p 3/2, then the excited state should again be 3/2 minus, but that is not the case for calcium 43. So this is one limitation of nuclear shell model. So the first excited state of calcium 43 starts at 5/2 minus. Then there are some other excited states before so for calcium 43, so this side is plotted in the unit of MeV, excitation energy. Okay, 3/2 and then 3/2 plus 5/2 plus 11/2 minus, and so on. Okay, so in order to explain these excitation energies, we cannot just rely on nuclear shell model. We have to do something else. So what has to be done is that instead of just taking one unpaired neutron, we need to take all these 3 neutrons into consideration to explain this particular phenomenon, this particular behavior of the excitation energies of calcium 43. Okay, so basically the answer to this question would then be the first excitation energy of calcium 41 is close to 2 MeV, while for calcium 43 has a few excited states with energies smaller than 1 MeV. So that's what we have shown here. So this option is correct, and the first so this is incorrect because it says that both calcium 41 and calcium 43 have low lying energy excited states with excitation energy less than 2 MeV. So that is not correct. For calcium 41, the excited state starts from this 2 MeV. Okay, and third option is also incorrect because it is saying that the first excitation energy of both 41 and 43 calcium are around 2 MeV. So that is incorrect, and this option is correct because the calcium 43 has many low-lying excited states below 2 MeV. That indicates that the extreme independent single particle shell model needs some correction, and that correction is of this sort that we need to consider all these unpaired neutrons and not just one unpaired neutron that we consider in the case of extreme independent single particle shell model. So when you watch this 7th lecture of week 3, then this entire thing is explained there, so you will understand it, and then if any doubt is there, any more doubt is there, then we can discuss it in the next assignment session again. So far what I have said Any doubt on this? Do you understand this question? Or should I repeat? Are there any questions? Okay, if not, let us stop here and then we will meet in the next week.